a vector potential and a scalar potential. The vector potential, for the vector potential, we know what is the curl of the vector potential, but we do not know what is the divergence of the vector potential. So vector potential is not uniquely defined. Then we have the scalar potential. The scalar potential depends on the vector potential because E plus dot T operating on A is equal to minus grad phi. So phi depends on A, and A is not uniquely defined, therefore phi is also not uniquely defined. So we defined two potentials and none of them is uniquely defined. We have some information on both of them. Now we need to uniquely define them or have some unique definition of these two potentials. So I will look at a Gauss transformation. So we'll look at a transformation which is going to give us a unique definition of these potentials. Now let us see an example here. We have two potentials A and phi. Let us say we change A and phi by adding some constant with this. Now if we add some constant with A, then curl of A now becomes curl of A plus some constant. Curl of constant is equal to 0. So curl of A is equal to B. Then curl of A plus C. C is a constant. That also is equal to B. So if you add any constant to A, you get a new vector. But on the operation, curl operation on A or curl operation on this new vector is also giving you H. So A is not uniquely defined in terms of H. Similarly for phi. This gives us more freedom. So in choosing how we are now free to choose the constant or anything that we can add with A and phi. We are free to choose that additional term. We are free to do that. This is called, since we have got more freedom, this is called Gauss invariance of the Maxwell's equation. This gives invariance to Maxwell's equation. Maxwell's equation does not change if we add anything to A or anything to phi, because A and phi are defining E and H. E and H define the Maxwell's equation, or they give the Maxwell's equation. Changing A and phi is not changing E and H. Since E and H are not changed, so Maxwell's equations are not changed when you change or when we add something to A or something to phi. So Gauss invariance of Maxwell's equation are possible. We get more freedom. Now let us look at some scalar function. As we know, E and H both are dependent on space and time. So let us consider a new scalar function f, which is dependent on space and time. So f is a function of RT, and we use the Gauss transformation, which is leaving E and V invariant. E and V invariant. The Gauss transformations are this phi dash or phi dash is equal to phi minus dot T operating on F, and A dash is equal to A plus grad F. So these two Gauss transformations we see. So what we have done is we have added the term minus dot Tf to phi to get a new potential phi dash. Similarly, we have added a term grad F to A to get a new potential A dash. We have got two new potentials A dash, phi dash from the original potentials A and phi. Let us see what are the effect. And we know A and phi are non-specific because they are not uniquely specified, they are non-specific. Now E is equal to minus dot Ta minus grad phi. So E dash will be similarly is equal to minus dot Ta dash minus grad phi dash. So E dash we can write as minus dot T operating on A dash is equal to A plus grad phi. So write that A plus grad phi minus grad operating on phi dash. Phi dash is equal to phi minus dot Tf. Put that. So on grad of phi minus dot Tf. Now expand this right hand side. That will give us minus grad phi, then minus dot T operating on A plus grad and dot T operating on F. That comes from the last term, minus grad minus grad operating on minus dot Tf. That gives us plus grad operating on dot TF. So now so that we get plus grad dot T operating on F. Then the second term minus dot T operating on grad F. So that gives us minus dot T grad F. Now grad and dot T are interchangeable. So grad dot TF is same as dot T grad F, because grad is a spatial operator, dot T is a temporal operator, so they are interchangeable. Their operation is interchangeable. So grad dot TF is equal to dot T grad F. We have a minus sign. So grad dot TF minus dot T grad F, each term will cancel out, leaving us 0. So E dash now becomes minus grad phi minus dot TA. We know minus grad phi minus dot TA is equal to E. Therefore, E dash is equal to E. So E does not change. So this shows that we have a freedom in selecting the potentials. Similarly, we can find out H, that also will not change. H dash will be H, that will not change, since E and H are related by E is equal to H by eta. So that way will not change. So we have got a freedom in selecting the potentials A and phi. So we have to impose some constraints between them. Now, since we have a freedom, we can choose it arbitrarily. Instead of choosing them arbitrarily, let us impose some convenient constraints between A and phi, and using those constraints we will select A and phi. So the imposition of constraint leads to something called Lorentz condition. The knowledge of potential functions A and phi, that gives us complete expressions for fields E and H that we have already seen, but unfortunately A and phi are non-specific. We know mu H or B is equal to curl A, and that gives us H is equal to 1 upon mu curl A. That gives us curl H is equal to 1 upon mu curl of curl A, and curl of H is equal to J plus dot T D. Therefore, 1 upon mu curl of curl A is equal to J plus dot T D. Now, I use this backcab rule or vector triple product rule. A cross B cross C is equal to B multiplied with A dot C minus C multiplied with A dot B. This is a vector identity. So curl of A will be the gradient of divergence of A minus del square A. So curl H is equal to 1 upon mu gradient of divergence of A minus del square A. So now that will be equal to J plus dot T operating on D, because curl H is equal to J plus dot T operating on D. Now let us look at the last term, J plus dot T operating on D. J plus dot T operating on D is equal to J plus dot T, D is equal to epsilon E. So dot T operating on epsilon E. Epsilon is constant with respect to time, take it outside the differentiation. So J plus dot T D is equal to J plus epsilon dot T operating on E. So that you can write as J remains as it is plus epsilon remains as it is. Dot T is now operating on E. E is equal to minus grad phi minus dot TA. So that we write. So the last term is minus dot TA minus grad phi, on which dot T is operating. Now that we can write as J minus epsilon dot square T operating on A minus epsilon dot T grad phi. So J plus dot TD is equal to J minus epsilon dot T square A minus epsilon dot T grad phi. We know divergence of just in the left hand side you can see divergence of A, so gradient of divergence of A minus del square A is equal to mu J plus mu dot T D. From where we got this? Because curl H is equal to 1 upon mu into this factor, multiply on both the sides mu, that gives us this. So that we can write as this is equal to mu j minus, now mu dot td, mu will be multiplied with dot td. Dot td we have found out as epsilon dot square ta plus dot t grad phi. So put that, if we put that, that gives us the right hand side will be mu j minus mu into epsilon into dot t square a minus mu into epsilon into dot t grad phi. Mu epsilon is equal to 1 by c square, c being the speed of light in free space. Put that, that gives us mu j minus 1 upon c square dot t square a minus 1 upon c square dot t grad phi. Now take everything, all the potential terms to the left hand side and the source term which is j on the right hand side, keep that on the right hand side, multiply minus on both the sides. So that will give us del square a minus divergence, gradient of divergence a minus 1 upon c square dot square ta minus 1 upon c square dot t grad phi is equal to minus mu j. So on that we can rewrite as two terms, combination of two terms or two factors. The first factor is del square a minus 1 by c square dot square ta, that is first factor, minus the second factor is on the gradient of divergence of a plus 1 upon c square dot t grad phi. So this is the left hand side, right hand side remains as a minus mu j. Next. So in the second factor, let us take the grad operator outside. So it is the second factor, first factor remains as it is. Second factor is gradient of divergence of a, gradient of two terms in the second factor. The terms are divergence of a plus 1 upon c square dot t phi, that is equal to, then the right hand side remains as minus mu j. Now we have to go and specify a. So specify a requires specification of divergence of a. Once we specify divergence of a, then we will specify a. Now we know that there is something called a wave equation which is of the form del square a minus 1 by c square dot square ta is equal to some function, some source function. So the left hand side is a function of space and time, right hand side will be a function of space and time. Here we are taking it as minus mu j. So this is usually the form of a wave equation. But we also have got this term del square a minus 1 by c square dot square ta minus gradient of two terms divergence of a plus 1 by c square dot t phi is equal to minus mu j. If we compare this with the wave equation, then we can say that in the second equation, the condition to get the wave equation from the second equation is the second term must become 0, or the second factor must become 0. Second factor will become 0 if the term on which the gradient is operating, that becomes 0. The term on which the gradient is operating is divergence of a plus 1 by c square dot t phi is equal to 0. So if that is equal to 0, then we get the wave equation. Now if this is equal to 0, divergence of a plus 1 by c square dot t phi is equal to 0, that gives us a definition for divergence of a. So the condition that we are looking for a, to specify a, which is divergence of a, that we have now got. So divergence of a is equal to minus 1 upon c square dot t phi. This condition is called the Lorentz condition. This is because of L Lorentz we have discussed it, not the Lorentz from which you get the Lorentz contraction. So this condition is used on A and phi, and this condition is called the Lorentz-Gauss condition. Why we use this? How we got this? By using the freedom to choose reasonable A. That freedom we have used, and divergence of A we have defined. If we define divergence of A in this manner, we get a differential the differential wave equation or the wave equation in A, and that is easy to solve. So we can solve for A. Once we solve for A, we can solve for phi. Okay. Now let us come to the radiation gauge condition. If suppose the A and phi did not satisfy the constant that we have just now defined, divergence of A plus 1 upon c square dot T phi is equal to 0, this condition they do not satisfy. If they do not satisfy this condition, then we will be trying to transform the potentials A and phi when this is not satisfied. The procedure for transformation is this. Use the Gauss transformation that we have defined. So the Gauss transformation is phi dash is equal to phi minus dot Tf, A dash is equal to A plus grad phi. So use this Gauss transformation. If you use this Gauss transformation in the constant del dot A plus or divergence of A plus 1 by c square dot T phi, then for A we will use now A dash, for phi we will use the phi dash. So that gives us divergence of A dash plus 1 upon c square dot T phi dash. That will be equal to, for A dash use A plus grad phi, for phi dash use phi minus dot Tf. So using that we get the two terms that is on the right hand side. Now we require appropriate choice of the function of f. If we have appropriate choice of function of f, then f will be the solution of an inhomogeneous wave equation. So we have to choose f appropriately. So when we will choose f appropriately, this will be equal to 0, the term del divergence of A dash plus 1 by c square dot T phi dash. If we equate that to 0, then the right hand term is equated to 0. That gives us divergence of A plus 1 upon c square dot T phi is equal to 1 upon c square dot square T f minus del square f. Now you look at the first equation and the last equation. First equation says that the constraint is not satisfied. This is not equal to 0, and using the Gauss transformation we now see that the left hand side is not equal to 0, but left hand side is equal to 1 by c square the square Tf minus del square f is equal to that is the left hand side is equal to this right hand side now. Okay. Now we know that from Gauss law, divergence of D is equal to rho, or divergence of E is equal to 1 upon epsilon into rho, because D is equal to epsilon E. And also we know E is equal to minus grad phi minus dot Ta, and divergence of A plus 1 upon c square dot T phi is equal to 0. These are three things that we know. Now let us find out what is divergence of E. Divergence of E is equal to divergence of minus grad phi minus dot Ta. Now that is equal to minus del square phi minus dot T divergence of A. Okay. So that is equal to minus del square phi minus dot T. Now divergence of A is equal to 1 upon minus 1 upon c square dot T phi if you use that. So that is this. So this you can write as 1 upon c square dot square T phi minus del square phi. So divergence of E is equal to 1 upon c square dot square T phi minus del square phi. Now let us consider this in the wave equation, in the Maxwell's equation. If we put that in the Maxwell's equation, then we know divergence of E is equal to 1 upon rho, 1 upon epsilon rho. So minus divergence of E, which is del square phi minus 1 upon c square dot T square phi, that will be equal to minus 1 upon epsilon rho. Similarly, we also have seen earlier for A, del square A minus 1 upon c square del square T A is equal to minus mu J. Both these are inhomogeneous wave equations. The first is an inhomogeneous wave equation in phi. Second is an inhomogeneous wave equation in A. Why we call it inhomogeneous wave equation? The reason is on the right hand side we don't have a zero term. If you have a zero term on the right hand side of this wave equation, so differentiation is on the left hand side. Differentiation is equal to 0 gives you a homogeneous equation. Differentiation is not equal to 0 gives you an inhomogeneous equation. So in that sense, this is an inhomogeneous equation. The density is rho and J. Rho is the charge density. J is the source density. These are the sources. They generate the potentials phi and A, and the potentials from phi and A we get E and B in terms of potentials. Therefore, rho and J are the source for E and B. So they are the sources for E and B. Now let us look at the significance. Significance is the Lorentz condition. We got divergence of A plus 1 upon C square dot T phi is equal to 0. This decouples A and phi. So this is a decoupling equation for A and phi. Vector wave equation, we have got del square A minus 1 upon C square dot square T A is equal to minus mu J by decoupling the Lorentz condition. Now A can be specified, A can be solved if J is specified. Similarly, for the scalar wave equation, we can solve for phi if rho is specified. So phi can be solved, phi can be solved if rho is specified. So the significance is it is simple to compute H and E once we know A and phi, and we can find out what is A and what is phi by solving the wave equation. Because once we know A, we can find out H. H is equal to 1 upon mu curl A. Similarly, once we know what is what is phi and A, we can find out E. E is equal to minus grad phi minus dot TA, which is equal to minus dot TA remains as it is. Now for phi, we can use minus C square grad A, divergence of A. We use that, then integrate that with time, that gives you phi. So that will be dot TA is equal to C square integration gradient of divergence of A over T, integration over T of gradient of divergence of A. So that is what is T. With this, we will take the next break, and when we come back, we will start with the other part.